and it's really a topic I don't like to talk about very much. I don't like to talk about anything that is particular element. And the reason I think this is really a bad topic to talk about is because looking at really black magic. And very much really dominated by superstitions which depend on the lab, the cost experiment, and the PI of the lab. And I have to admit that myself also still have superstitions which I can't explain to you why I believe in it, but it has worked for me, and therefore I do. And so a lot of information is really distributed by this kind of hearsay. So he said it works, and therefore I try it. But it's never really solid, proven, published. So there's a lot of rumor around. And so for me, it's almost a kind of an anecdotal science. So if you hear something, it's worth trying it. And also, in our field, very often, almost all the time, we only really report in papers the successful experiments. And we now tell you a lot of things we tried which no worked. And so it would be really useful if people would describe every experiment they tried and which didn't work. Maybe would actually find out that some of the things we constantly do never work. But of course, this is a problem to actually publish negative results. And then there's a word limitation and complications, so you don't want to waste it, so you wrote some things that didn't work anyway. And so, it's a workshop. And I'm just one of the people who do two-dimensional crystallization. There are a lot of experts in the room who also do 2D crystallization. I think it would be really good if people would actually contribute to this talk and really challenge what I say and say, for us it's completely different. Because it's going to be different for every lab or not. And so I haven't really produced or really rehearsed this talk because I really hope it's going to be more interactive and people start to chime in. And so the very obvious, which you will see quite often, you start with your membrane protein, you solubilize detergent, and then you add a few lipid molecules, and you try to add very few lipid molecules. And what you try to create are so-called mixed micelles, where you have the membrane protein surrounded by the lipid molecule, the whole thing solubilized in detergent micelle. Then you remove the detergent, or you lower the concentration below the CMC by dilution. And then, once you remove enough detergent, what you hope to end up with is a thinner layer of crystalline protein, membrane protein. And so this looks very simple and straightforward on a slide, but how this really occurs is actually not clear at all, or at least not to me, and so maybe other people have a better idea how it happens. I usually see it as a two-step process, but it's also been proposed to be a one-step or a three-step process or a mixture of anything. And so basically, once you have your protein mixed with lipids, you get these mixed micelles. And then basically not much is happening as long as you remove the CMC until you actually really reach the CMC. Once you get kind of a lack of detergent. And then what happens is that these structures, these mixed micelles, actually start to fuse with other lipid protein detergent structures. And you end up forming a bilayer if you're lucky. And this bilayer still has a lot of detergents in it. So it's very fluid and flexible and things can move around and can align to each other. And then if you're lucky, you actually start to form nuclei of proteins coming together, making productive interactions. And then as you remove more and more of the detergent, you get a further ordering of the protein to actually end up with a two-dimensional crystal. So in my view, it really first the reconstitution of the protein into a lipid bilayer, and then a second step, you order the protein in the membrane. But it can also happen that you basically go directly from this state to this state, you get it in the membrane, it's immediately crystalline. Or another possibility is you first form the lisosomes of the membranes, and then later on the protein actually inserts into the membrane, and then yet again later the protein actually starts to crystallize. What really happens is not really clear to my knowledge. And I think Andreas Engel has done quite nice experiments a while ago trying to figure out what's actually happening, but it's not really nailed down what the crystallization process really is. And so basically we have a system, kind of a trivial system. We start with protein in detergent, we add lipid also in detergent, and so we have this interaction between protein, detergent, lipid, and protein. And these interactions you can modify with the buffer that the whole thing is in. And so then simply removing detergent should actually lead you to two-dimensional crystals. So one way to think about this kind of interaction is to think how strong are these interactions. And so, for example, if the protein-detergent interaction is much stronger than the lipid-detergent interaction, if you start to remove the detergent, you first remove the detergent from the protein, if this interaction is stronger than this interaction, you start to remove the detergent from the lipid, you start to form antivesicles, then all the lipid is used, now you remove the detergent from the protein, and you just end up with aggregates. So that's not very productive. On the other hand, if this interaction, the lipid-detergent interaction, is much more solid than this interaction, then you basically start to remove the detergent from the protein crashes out of solution, now you remove the detergent from the lipid and get empty vesicles. And very often if you make two-dimensional crystals, you actually end up with these kind of situations where you have lipids, vesicles empty, and protein lying next to it. Now, ideally, you want to have a system where the protein-detergent interaction is about the same as the lipid-detergent interaction. So now you remove everything at the same time, and the protein can actually start to interact with the lipid. And so then you basically get protein-lipid interactions, and if you're lucky, you get nice lipid membranes that protein crystallized in the membrane. But you can also end up with very heterogeneous lipid-detergent aggregates, which look very messy and don't help you either. So this is one way to think about this, and I think that Engel's lab really thought a lot of these terms and came up in the end with very nice new terms. But for me, I can't think very well this way. For me, it's not very productive. So I don't quite understand if you have actually mixed mice and you have all these interactions in the same kind of complex, and then how do you think about the lipid-detergent interaction versus protein-detergent interaction? So this is kind of all things together, and we actually don't really know how mixed mice really looks like. So that's also kind of difficult to understand why a detergent should interact differently with a lipid than with a protein, because most are just hydrophobic interactions. But there are different interactions, and it does actually make a difference. But for me, it's very difficult to think about what is actually determining these interactions. So I decided, for me, this is not a very fruitful way to think about two-dimensional crystallization. I'm a biologist, I'm interested in the protein structure, so I'm going to approach this completely different, to talk about the system and each of the components and how we think about it. And so probably a lot of you think differently about it, and it would be interesting to actually discuss this. And so the protein is obviously the thing that you're most interested in. You want to understand the protein structure. So this is a given, but there is a kind of a thinking that pure and homogeneous protein is better if you want to make two-dimensional crystals. And there's no discussion about it, it's certainly true. But a homogeneous protein, if you have a single band on your gel, actually doesn't mean that you have a homogeneous protein. You can still have a protein that adopts different functional states and can have different oligomeric states. So you actually want to really understand the protein both on a functional level, so you want to lock into one functional state of the protein, and you also, if you can, you would like to lock it into one oligomer state, and quite often you have dynamic equilibrium between different molecules. So you would like to have a pure homogeneous preparation, but it's actually not 100% necessary. So first of all, you can very easily check in the microscope your protein solution. Even if the protein is too small to really see it, at least you can check whether you have aggregates in your protein solution. Then what actually happens when you crystallize it, you take it out of solution, and so you actually push it, you play with the equilibrium. So if there is one state, functional state that crystallizes, you actually take it out of the equilibrium, and it can fall into this same state, and so you can actually end up crystallizing one state despite the fact that you have different functional states in solution. The same is actually true with oligomers. So even if you have a mixture of tetramers and dimers, for example, if you only crystallize the tetramers, the dimers will tetramize and then also go into the crystal. So I believe it's nice if you actually have a very homogeneous solution to start with only tetramers, but if you have a mixture of dimers and tetramers, it doesn't mean that you can crystallize the protein. And something which was very interesting to me, which I didn't expect, at some point I actually had a fairly impure protein preparation with a lot of contaminated protein. I didn't know that I just made 2D crystals, and what I found in the same membrane are actually patches of one protein crystalline and the other protein crystalline in the same membrane. So it seems that even if you have the early protein, you can still get 2D crystals. You will never be able to reproduce it, but you can get 2D crystals. So if you have, what I believe in is that if you have higher oligomers, you have a better chance to get two-dimensional crystals. And the idea is that higher oligomers, for example tetramers, have already kind of a square shape or a very defined shape. And so you have a building block that is much easier to get into a two-dimensional crystal arrangement than if you have a single protein with a very asymmetric shape. So what this means is if you have a dynamic equilibrium between a dimer and a tetramer, one on a dimer tetramer, you would actually like to try and push it into the higher oligomeric state for crystallization purposes. Now, unification types is another thing. So they have a good thing because so the question is, do you want to leave them for crystallization, or do you want to leave them on, or do you want to leave them on for 2D crystallization? And to leave them on has a good thing because they increase the solubility of the protein. The reason you want to take them off is because they can interfere with your crystal contacts. So, to my knowledge, 2D crystals have been obtained both with and without tags. But in our case, very often we actually have to remove the tag to get the bit higher order crystals. And again, this is anecdotal, this is what we experienced, but there's art to understand how it works in other labs. So this would be an opportunity for you to share your experience. Do you cleave your tags, do you leave them on?
I think not personally, but I think one that we remove it. The clips better usually.
So that's 2D crystallography. The reason there's control is every lab believes in something else.
No, but I have good vision.
Yeah, you put one already, okay.
Also, if you have an interterminal receptor which is too long, for example, there's a girl she has been getting crystals of 4, 5 angstrom, 2.8. She cleaned the interterminal, now she goes beyond 3 angstrom.
We have the same experience with upper power 9. But then again, if you have other proteins, you actually have large extracellular membranes domains and crystal contacts into those. You don't really care whether something is bonding out on the other side. Basically, the idea is you're trying to do both. You try a little bit without cleavage, etc. And one thing that becomes increasingly clear is that homologs of the same protein from different species and behave completely differently. So one thing can never crystallize the other thing from the homolog crystallizes immediately. So if you're wasting a lot of time trying to get crystal with one protein homolog, it's worth trying to express the other homologs and try to make 2D crystals of those. That's very common in crystallography, almost everybody does it. So the next thing is the detergent.
Sorry, excuse me. Could we say that hydrophobic proteins mix more well out of 2D crystals than proteins that have a large homogeneous domain?
Based on how many examples?
Pepperins, H2.
But there were very nice crystals of ATPases.
But it was from native mass.
Okay, what people think.
But it's a real question.
Yeah, it's a good question. And it's just to show you the extent of our ignorance. We really don't know much.
You know, the hydrophobic patches are non-specific, while the hydrophilic areas by ionic interactions or other electrostatic interactions are very specific. So I would think that just conceptually, the more hydrophilic areas, surface areas you have, the more stable or more well-defined your crystal interface is. But intellectually, I'm not saying that's the evidence that we have, but just intellectually thinking about it.
Except that in upper point 4, it's actually interactions are made in the transmembrane domain and it's very specific interactions.
Through lipid or directly?
Directly. And then again, upper point 0 basically has no protein-protein interaction, only protein-lipid-protein interaction. So how do you think about this now? I can't understand at all. So it's really, we have real lack of knowledge in many areas.
Yeah, I don't understand that for the HIV capsid protein, it's basically soluble protein. It's made very good 2D crystals, it turns out, but it all has to do with, like you said, specific interactions. So sometimes I think the biggest problem for membrane protein that has a have a hydrophilic domain. All kind of domains are not have specific interaction with each other. That's why it's turned out normally more important to have the hydrophobic part is playing a bigger.
I definitely think it's easy to get good structures out of proteins which don't have a large hydrophilic. Simply when you absorb them on the grids, you get a lot of distortions, the excess elements, so you get the best resolution in the membrane. So I don't know whether we might actually have very good crystals with large excess domains, but we never see it because we just simply squash them.
No, it's a good question. From my experience, it seems that when you try to use protein without a common organism, and you often have membranes that stick together. So the protein is upside down, and then you have hydrophilic interaction from proteins that are under different layers. And you have stacked. You may have stacked by layer.
But then again, this VDAC, which has very little excess membranes, makes massive steps.
Right.
So anyway, this is simple enough. Okay, so the next thing in our diagram is the detergent, and that's basically determined by the protein. You don't, the lipid doesn't really care about the detergent, but you choose the detergent to make your protein happy. And so a lot of people actually take a lot of care about the solubilization efficiency of the detergent. You want to get as much of the membrane protein out of the membrane as you can. But I really believe that the solubilization efficiency is really secondary. And what you really want to look for is stability of the protein, that you don't denate your membrane protein. And for us, in terms of dialysis, the high CMC detergents are easier because you can remove them much quicker. So, but high CMC detergents are usually harsher. Now, this is a real issue in X crystallography where you have to incubate for many weeks or months to get 3D crystals. But in our case, we actually add lipids very quickly after we purify the membrane protein. The lipid has a massive stabilizing effect on your protein. So we can actually avoid the slight offshore detergents in X-ray crystallography because the membrane protein is much more exposed to the detergent. And I really believe that you should not care very much about the stabilization. Of course, you have to get some protein out of the membrane. But if you get all the protein out of the membrane, but it's immediately aggregated, it doesn't have to be a thing. However, if you can only get 20% of your protein out of the membrane, but it's a perfect condition for 2D crystallization, that's much more important. So don't get too worried about the solubilization efficiency. And then there's again, now we again come into this superstitious field. So at some point, it was suggested that detergent mixture might actually be quite good for 2D crystallization. That you should use a high CMC and a low CMC detergent. And for me, this now really made a lot of sense because if you have a mixture of detergent and you start to dialyze, you first remove all the high CMC detergent where you have still a lot of the low CMC detergent in your sample, and then slowly remove the low CMC detergent. So what was the point of ever having the high CMC detergent? So I don't quite understand the idea of these detergent mixtures of high and low CMC. But the specialist might have an explanation for that.
Well, yeah, the idea is good, but of course, as you said, you have to remove the both detergent together. This is what Dialysis does.
Okay, so it might be good for Dialysis.
But just
So, no, maybe from what I know from the mixture of detergents, it has been used, for example, in 3D or purification of GPCR or EBC transporters. And there is a normal detergent, let's say, low-stigmatosite, in addition to something like SHAPS or cholic acid or some kind of detergent that looks like cholesterol. So, and they are not used at a concentration above the CMC, but well below. And we may consider that it is like a protective agent for those proteins mimicking the cholesterol. From what I have understood from the GPCR paper.
This is a different thing I was talking about, there's muscles idea of mixing detergents.
But the mixing of two detergents above the CMC.
When I try to extract a high CMC detergent, the extract for Russians, yes, but we can add both two, the stability of protein both. So I think
So for solubilization, it might make a big difference.
Again, I think here we address I mean, I think probably chaps is there, lipids have been taken away. Chaps solubilize the lipids, and there's and protein is in an island of lipids, surrounded by lipids, and this is not suitable for quick dissolution. The chaps is obviously it's a weird detergent. Also, when you look at it in the microscope, it's strange. It's also used for GPCRs, a mixture of chaps and medium. This is the mixture many biologists use. We find this protein is still alive, but this is not suitable for destabilization. Chaps is a strange guy. But again, the thing is that it hasn't been tested yet. But again, with BioBeats, you can do that. You could do that. That has not been tested yet extensively because BioBeat is not. It's also difficult to not everyone master BioBeat experiments. And this is difficult.
Robin Bosch had this idea of putting low CMC detergent in 95% of the CMC, so that you can remove the high CMC detergent quickly and then for a longer period of time stay just below the CMC to soften the membranes to allow some flexibility. Made us to do that, right? Long time ago.
But basically, I don't know real high-resolution 2D crystals that were obtained with mixed detergents. That's just another kind of these superstitions that people bring out, and it's difficult to think about. That's another one that I read in literature that never made sense to me, that you want to start with a high concentration of your detergent, much higher than your CMC. And it would create larger 2D crystals. I can't come up with any reasoning why this would happen. Because the only thing when something happens is that CMC and how much detergent you had before, it doesn't really matter. The only thing I can imagine is that when you have a lot of detergent, the dialysis is going to go much, much longer. So you have much longer time that you might actually be able to form mixed mice cells. But then rather than just starting with a high initial detergent concentration, you could actually just start with a pre-incubation with your detergent program.
What is your above CMC? 10x, 20x, 100x, 200x?
I don't do that. But
Yeah, but in the literature, as I've been trying to
I think it was about 10 times.
10x of the CMC.
Sorry to speak again, if Andreas would be there, he would probably say something about the amount of initial detergent concentration. What he thinks is that, okay, I'm not Andreas, but let me try to reproduce what he says. And I believe that this is true, is that sometimes when you need a lot of detergent to solubilize a protein, that means that your protein may not be in so good shape. That means the detergent has to cover the unfolded and offbeat part of the protein. And that might be a bad sign. That's why when you need a lot of OG, this is not because it's high CMC, but also because the OG protein is not in good shape, and you need a lot of it to keep it alive.
Well, it depends on the protein. I mean, other products are very complementary.
I don't really understand the story of initial detergent concentration with the solubilization, because after solubilization you have the purification step, and almost all people are decreasing the detergent concentration during the purification step. So even if you solubilize at 3% of OG, then on the ANTA column you will go up to 1.2, so then you have the normal detergent concentration for the crystallization point.
Yeah. The idea is to check, go lower as much as possible to see when your protein is aggregating at a lower level, and 1% is still a lot of detergent.
But But anyway, basically they agree that high initial detergent concentrations don't make much sense.
But doesn't this all depend on the initial amount of protein and the protein concentration that is present? If you have a very dense pellet, you actually need a lot of detergent. Then the CMC, for that matter, is irrelevant, but you need a high concentration to actually solubilize all your protein.
Yeah, I'm actually not talking about solubilization, I'm talking about 2D crystallization. That a high initial detergent concentration of the purified protein would be good for getting bigger crystals.
So then you mean you actually add again more detergent after the whole purification step. So you have it at X detergent, and then you add more before you crystallize.
But you might get some unfortunate information how much detergent you need to keep your protein alive. That I think is important. And I think that has nothing to do with superstition. It's something you can check out.
Yeah,
For example,
it's not superstition. Once you measure it and you have experiments, you actually document what you find. But in the moment, it's superstition. In the moment, it's just hearsay.
You know what? While doing dilution, sometimes I needed higher initial detergent concentration to go. I wanted to have as low as possible, but I needed to add more detergent because the protein needed. And of course, the protein concentration was also an important factor to master. It was critical to the dilution method.
Okay, so let's move on. So the next one is the lipid, and that one pretty much can be freely chosen. The question is how crucial is the lipid ability to get to ecosystems. And I think that is very dependent on your proteins. So some proteins only crystallize in one lipid, nothing else. Other proteins of performance in particular can pretty much crystallize in whatever lipid you fancy. So that is, again, you don't really understand much what drives why a particular protein needs a certain lipid or why a protein doesn't care whether it has lipid or not. A certain lipid or not. But it is another thing, the phase transition temperature. And obviously it influences the membrane fluidity. But you actually have a protein there as well, and once you have a reconstitution mixture. And so once you have a protein there, you don't get the nice dense packing of the tails that you have just with lipids. So then the question becomes how important is really the phase transition temperature anymore, because it's never going to be crystalline. And we actually just made very nice two-dimensional crystals with a lipid that has a phase transition temperature of 50 centigrade. And we had it in room temperature. So I'm also convinced that you will have to be so careful about the phase transition temperature of the lipids, because you have the protein actually also there. Don't bite me.
Bite me. No, there's again the students.
Is experiment person or is what you posted?
It's really
For example, the MPC recently we get better crystal by heating beyond 25 degrees. Usually, the biggest request when I built my first machine was, can we eat this? Can we? Because people get their best crystals putting their buffer. This is buffer at 37. I built the machine, and they get indeed the crystals by putting it in the machine at 37 degrees.
How reproducible is this? Did you do this once and then you got bad crystals, or can you actually take the same sample and run it by fluid temperature?
It has been making difference in at least 2 cases. And for I've been working over this 1 year. I've been asking for this heating thing, and in all that 23 degree was making a difference, but that was superstition until I did the thing. I spent time putting the heating device.
You're the one guy I believe actually.
Because and it makes a difference by just pushing it to 37 degrees. Maybe 37 is too much, not enough, we don't know, but now the crystals are better in 2 cases, case of a toxin, in case of a protein.
So we did 0.0 room temperature DMDC plus 1.9 angstrom without any play with temperature or anything. So
It depends also on your room temperature. Our room temperature. No, the room temperature in the lab can vary from 20 to 25 degrees where the things are, depending on where you put the buffer in your room.
So just my frustration with all this, I talk to you, I hear this. Can I read it in any paper? I increased by 3 degrees and made better crystals. You can never read this kind of thing.
They're finishing the master. I should write.
We have a lot to solve to actually. Anyway, so this is another discussion that we just had. Do we make the lipids fresh every time, or do we make a stock solution? And the issue here is lipid oxidation, which you obviously want to avoid. But on the other hand, reproducibility is probably much better if you once make a stock and then you use the same stock again. Actually, adequately it and then freezing it might be a very good idea, that you can get both. But we always make a stock solution and keep it and run it, use it for about 2 months, and then we make the next one. And the reason is that reproducibility is really the killer in 2D crystallization, in my opinion. I completely gave up the belief in reproducibility in 2D crystallization. And I'm going to talk about this later on again. And then again, do you want to use single lipids, do you want to use lipid mixtures? I think the basic idea is always you want to start easy and simple. So we usually use simple lipids, and usually we also use equal lipids. But you can always get more complicated and start to mix other lipids in and get different ratios. But initially, I think playing with single lipids is a good idea. And then the next question is, how do you actually prepare the lipid? Do you have it in water with detergents, or do you have to buffer the detergents? I mean, there's subtle differences, but if you then add the lipid to your protein solution, change something again, and that again affects your reproducibility. And because reproducibility is so bad in 2D crystallization to begin with, I think differences like this actually might add up in the end and give you differences in the results and the outcomes of your experiments. And then the next question, in what detergent do you actually solubilize your lipids? If your protein is solubilized in diamortisate, you would like to solubilize your lipid also in desmortisate, but this doesn't always work. So then we add in a little bit of OG to get it solubilized, and once again you have changed again something. Really making it hard to get it really nailed down the conditions that you're looking at. And these are all tiny little things, but they all add up, and in the end we really get into trouble.
For the single lipids or mixtures, could you comment if there's a difference between, let's say, bacterial or eukaryotic extraction or overexpression seems? Is that the feeling that the more complex the organism comes from, the more complex the native membrane is, and therefore you might actually need to take that into account?
That's a good point, but I think once again it depends very much on the protein. Aquaporin is a membrane, and the main membrane protein doesn't have a lipid in. Other membrane proteins need a particular lipid even as a cofactor, so that one needs to have it. And then there's probably everything in between. And something that I always thought would make a difference, should make a difference, is the length of the acyl chains, because that determines the thickness of the membrane. Aquaporin 0, we can take all kinds of different acyl chains still make 2D crystals, which doesn't make any sense to me. So it's very difficult to rationalize what you should do. And so in the end, it's basically a really just a find out game. Are they?
Yeah. No, as a guideline, when you start dialysis crystallization, you use high CMC detergent, they're harsh, and so within minutes they go to some kind of your solubilized lipid easily, and you go to some kind of equilibrium really rapidly. If you try to install a lyser to, for example, the LSDBN, you have to wait a couple of hours until it's well solubilized and your lipids are solubilized. You even have to put them at room temperature, that it's not no gel phase-like anymore thing, So after right after you make the detergent mixture, you should not remove the detergent too fast, and I think that may be a kind of guideline which is important. And now it's up to anyone to maybe decide how he wants to wait. But don't wait maybe until you have a equilibrium. Maybe someone may say, and I will agree with him, that sometimes misequilibrium may lead to good crystallization. So again, there is no rules, but one should think I should wait or I should not wait. But at least, as you say, you have to remember what you have been doing. You have been incubating your sample before you start to remove it.
Okay, so.
And what would be to change the temperature during the dialysis? So to start at 18 degrees and then move to a higher temperature?
Yeah, we can do that as well. So that's why to get a difference. So detergent removal, there are different ways to do it. Dialysis is still the only way that you have produced 2D crystals that went to atomic resolution structures. All the other methods have not yet actually produced such a structure. And something you should keep in mind, and I think it's really kind of sad that this very old technique is still the best thing we can do. So you will contradict me again.
I don't have 1.9 extra.
I would be happy with 3.5.
What, in the fund structure or projection map?
Projection map would be fine.
Good, then you're happy.
Okay, so
Yeah, no,
you're writing it up once you have your masterpiece as well.
No, I will show this afternoon. Actually, it's a master thesis. It's a Makul, right? Makul Yazini.
That's what?
Makul Yazini, this is his name. Makul Yazini, a master student, actually was hired for to program, and he gets beautiful. Is it? If you help me to write it, then.
Anyway, so now there is one high resolution crystal that was done differently from dialysis. So far everything that's published has been done with dialysis. Then I'm not going to talk much about this. Dialysis is the next method that was used. I'm not quite sure about absorption of protein also and lipids to the diabetes, but you will probably talk about this. It's particularly good for low COC versions. Dilution, I think, is a very interesting concept, and how they have actually developed that. The one thing I don't know is if you have a very low CMC detergent, as you dilute your sample, you dilute your protein, and you end up with a very low protein concentration, and then it becomes difficult for protein to find each other. So I have a problem with the concept, but the next thing he did, the chelation, I actually think is great. And the tuticals he actually showed in the paper are very, very nice. But I don't remember, you never did anything with them. So, but anyway, chelation I think is a great thing to do, but it hasn't really been used widely. But that, I think, is one of the new techniques, because you can very nicely actually control the removal of the detergent. The 2D crystals, just one thing for the new people. Everybody looks for size. You want to have big vesicle. Size doesn't really matter all that much. What you really want are well-ordered crystals. If you have small patches of very well-ordered protein, you can do a lot. If you have large arrays of not so good ordered protein, you will have limited resolution no matter what. So you should really look for the order. If you want to do electron diffraction, you would like to have a size of about 1 micrometer or so, or larger. But again, you don't care that the vesicle is 10 micrometer. If the vesicle has 100 little patches, which are not coherent, the whole size doesn't matter. So what you need are coherent areas of 1 micrometer. Then you get different types of membranes. Out of 2D crystallization, you can get sheets, vesicles, and tubes. Sheets is really what makes you happy, because that's well fit for high resolution structure determination. Vesicles have issues with electron diffraction, but you can actually use vesicles to do functional assays, and that's something I like, because you can actually you make a crystal, and at the same time you can use the vesicles to do functional assays. You can prove directly that the protein in your crystal is actually active. And then tubes. Advantages, you don't need to tilt the specimen in the microscope, but it's very hard to work with them to get to high resolution. So tube is, in a way, that sentence. Yeah, you can just.
I don't do any invisible.
Okay, and then there's a real issue, and that's stupid, in my opinion. It's a really stupid issue, and that's stacking of membranes, as we just discussed previously. Much more frequent than you think. If you make 2D crystals and sheets, they actually start to stack on top of each other, and that kills you, absolutely kills you, because if you just have two layers, then it's fine. But if you have a variable amount of layers, then you're in big trouble, because you can't merge the data. So that's really pick up the speed. So certain things that we do when we actually do the experiment, one thing that I believe is very important, you try to minimize the time between solidization and the time you add the lipid, so that the protein is exposed to the detergent at the shortest possible time. You want to determine the protein concentration with much care. It doesn't need to be an absolute value, but you need to be confident that you always measure the same value, because that will really affect your lipid to protein ratio, which I believe is one of the most crucial variables when you try to make 2D crystals. Liquid solution we have talked about before. Take an example. I think when you screen, you should have ideally a protein concentration of about 1 milligram per ml. Don't go below 0.5 milligram per ml. We sometimes get crystals at this concentration, but usually not. So you need a certain concentration in your sample of protein and lipid can find each other to actually make nice 2D crystals. So that is another thing, this pure conjugation that we talked about. if you have low CMC or high CMC detergent, it might be a good idea to let it stand for a while so you can actually have an equilibrium. If you have low CMC detergents, the dialysis is going to take so long that you probably don't have to pre-incubate because it takes a long time to get to the CMC. So there are different dialysis devices. The most sophisticated one is this continuous flow system where you have where you can control the temperature and all these kind of things. We quite often use very simple dialysis buttons. Then there are stabilizers which give you a large area for dialysis. But this gives you actually, if you have low CMC detergents, these might be very nice. Hockey sticks have been introduced by Vancouver, but I'm not sure if they're used. Still used? So once again, superstition has it that makes a difference which method you use. So Henning told me that when he uses the system compared to the dialysis options, with the machine he gets better 2D crystals. And that's again an observation, which I don't know. So it would be great if we could actually really do defined experiments to figure these kind of things out. Because these are tiny little details, but they might make a difference sometime. And the dialysis membrane usually have 12 to 40 kilodalton. You should prepare them by boiling an ETTA. They come with heavy metals in the dialysis membrane, so you want to get rid of this, so you want to use EDA. You also boil them in ethanol to kill the bacteria, and then you store them in ASA. Sample size is another kind of area of conflict. If you take small sample sizes, you can screen a lot of conditions. But then you only have a small sample, and that's all you get, and you won't be able to get a structure out of it. On the other hand, if you make big samples, for example 50 to 100 microliter samples, you can screen much fewer conditions, but once you have a 50, 100 microliter sample, you can go and determine the whole structure. And that's what you actually did with Optifine 1. You had one bottom of 50 microliters and you got a structure. You could never reproduce the same quality of crystal, so if you started with a small sample, you would be really frustrated at that point. So that again, a philosophy, what do you want to do? Do you want to risk that you can reproduce it, or whether you want to go for the lucky shot and then you have everything you need? The dialysis buffer composition, a lot of stuff that influences it. Something I want to point out, we have all those crystals at slightly acidic pH. We actually almost never try at slightly basic pHs anymore. We always go to pH 6 roughly. The available contaminants can have an influence. Magnesium always has less. Calcium and magnesium often have the same effect, but calcium usually has a stronger effect than magnesium, so it does the same thing at a lower concentration. So we usually use magnesium so we have a finer control. Dialysis speed is another thing that we talked about, and the basic idea, a very basic idea, is that if you have a slow dialysis, you basically grow fewer crystals with a good order and larger crystals. If you grow your crystals very quickly, you get more crystals which are smaller and have less good order. That's the same negative crystallography actually. And so it's nice if you can play around with the speed at which you dialyze, but that's not so trivial. So way to do this is you can change initial detergent concentration, but that is not what I think is a crucial thing. I think the crucial time is when you reach CMC and the amount of time that you stay at the CMC. And so if you have low CMC detergents, you actually stay much longer at CMC than with high CMC detergents. But nevertheless, a lot of the very well-ordered high-resolution crystals will actually obtain with octaglucoside. So now you figure out what you want to do. The dialysis speed also depends on the cutoff of the dialysis membrane and the size of the dialysis membrane. Buttons give you always a slow dialysis because you have a very small area to dialyze, while slidalizers or dialysis tubes give you a much faster dialysis. And then another thing that you can actually do is change temperature, or you can actually also dialyze against the dialysis buffer as a detergent as its CMC. And we did this once, and this is again an anecdote, but when we did this for a particular protein, we actually ended up with much bigger crystals. That's something that might be worth trying. when you stop the dialysis, once the button's turned, they become opaque, so you start to form vesicles, then let it run for another 2 days, so that you will remove all the remaining detergents. And this is screening, so I think I should stop here. So all this is kind of basic stuff. But the idea is really, I mean, a few things that I really want to, I think this is, you can just look at it at the hand. But what is important is that people start to talk to each other and to really figure out what matters and what doesn't matter.
I think you have been showing aggregates. I think it's important for people who are going to aggregate to have a look, and because even in all that, some people are losing so much time because they look at aggregates and are these the ripples from lipids. If you can have a word about this, I think it's important.
Okay, so this is a typical outcome where you have a lipid protein aggregates. If you look at this, just take the grid out, don't spend time looking further at it. Even if you have a vesicle every now and again, you really don't care. That's not a good outcome. So once you see this, remove the grid from the end. These are membranes, and you can see that you have aggregates next to the membranes. And that's a very common thing to have. So once you have aggregates, it doesn't mean at all that your sample is not good. Sometimes, if you have rims of aggregated protein around your membrane, it's actually a good sign that you have probably very good crystals. These are not good membranes because you can see you have aggregates on the membranes and so on. So this again, you see it, you take it out, you don't really waste your time with it. Now this becomes more interesting. Now you have very nicely flat membranes. And this actually works to go and try and see whether you actually have crystals in these little membranes. So now you start to actually really invest time in checking these kind of samples. Once you have membranes like this, you're happy. Usually this is a very good sign. If they have a good shape, it doesn't mean there must be crystals in there. You don't know the quality of the crystals, but this is a very good reconstitution. Even though you have a fairly significant amount of aggregation, there's a good chance you have good crystals in these. So when you have small vesicles like this, you're actually not worse off than if you have big vesicles like this. But because what you need are large flat areas, and although this crystal is much bigger, you have a lot of folds. So this vesicle, although it's big, is actually no better than these vesicles. If you find something like this, it's interesting to look at vesicles. So this is what you really want. I mean, these are the perfect crystals. You can see very short batches and very defined shapes. There you can almost, just from looking at the membrane, you know that this is a crystal.
When you see those vesicles, what do you do afterwards with your sample? So you saw the vesicles, right? You know you start forming the crystal, right? So which variation you go now? Do you change the protein? What do you start doing? Because you know at this point you got something, right? Oh, it's a big conversation, okay?
I mean, we have 3 times that we talk about 2D crystallization. And so maybe I can just pick up and talk about this, because I think discussion in this 2D crystals is really the bottleneck of all of what we do. And I don't have any great ideas how to get better 2D crystals. And so it would be a good thing for people to discuss and actually come up with ideas and write up what they find.
But not now. No, yes.
Okay, so let's just go for lunch and do something.
We are off to lunch now. I actually have to walk everybody over there. They're going to be giving us the meal tickets at that place. I should let you know that they don't have lockers over there for your bag. We will be locking the system though when we leave, so you can leave your stuff in here. And they shut the place down at 1, but we should be fine to keep eating until 1:30. So.